If you're not confused by infinite dimensional Hilbert spaces in quantum mechanics, then you probably don't understand what's going on. This is the part of quantum mechanics that somehow people are less concerned about, but is actually a minefield. There are really big issues there. You've probably heard about eigenstate of position momentum. Well, they don't really exist. They're not in the Hilbert space. You might think that the Hilbert space for a continuous quantity like position and the Hilbert space for a discrete quantity like number of particles is different. Actually, they're not. You may have heard of rigged Hilbert spaces and wonder how exactly they're cheating. Well, we're going to look at some of these things. We're going to see what it means to generalize the case to infinite dimension, how observable actually work like that, what exactly is a Cauchy sequence, and a little bit of Stamper distribution. But I warn you, by the end of this video, you'll probably be more confused, because I'm confused, because there are actually issues there. It's really a minefield, and my hope is that at least after having seen this, you'll be able to avoid the bigger mines. So let's get started. Let's start by looking at a finite dimensional Hilbert space. In that case, we have a basis which we can understand as the eigenstates of some operator, and the basis span the whole space such that any other vector psi is a linear combination of the vectors of the basis. Now, the idea is that we want to take this and generalize to the infinite dimensional case. Essentially, we want n to go to infinity. The issue is that there is no single way to do it. We have to establish a criteria that tells us which infinite sums are allowed and which one are not allowed. And so Hilbert spaces solve that problem in the sense that it gives us a mathematical condition, and we'll set aside the question of whether that mathematical condition is actually physically meaningful or not, but at least it gives us a mathematical condition that tells us which type of infinite sums are allowed, which one converge in the Hilbert space. So what is the Hilbert space? The Hilbert space is a vector space, so that is, we can make linear combination. It has an inner product, which means for quantum mechanics we can calculate probability, and it is complete, meaning that it contains the limit of all the Cauchy sequences. And this essentially is telling us which infinite linear combinations are allowed, the one that are a limit of a Cauchy sequence. Now, this requirement is redundant for finite dimension, because if you have an inner product vector space, automatically all of the Cauchy sequences, if it's finite dimensional, automatically all the Cauchy sequences converge in the space. So the idea is that by assuming these conditions also for the infinite dimensional case, we make the inner product space behave a little bit, in some sense, as if it were finite. So then we have something similar. And some of the intuition that we had for finite dimensional cases are going to go and extend to the infinite dimensional case. Okay, so now we need to understand what a Cauchy sequence is. Before talking about a Cauchy sequence, we need the idea of a distance function. We need to show that the inner product introduces a distance function. A distance function mathematically is something that takes two elements and tells us how far they are apart. And there are some conditions on this that the distance function has to satisfy. If you get the distance of an element with itself, then the distance has to be 0, and if you take two elements that are different, then the distance should not be 0, should be greater than 0, should be positive. You need that the distance is symmetric, so that if we change the order of psi and phi, we get the same result, and it needs to satisfy the triangle identity. So if under those conditions we have a distance function, and the way that we can get a distance function from an inner product space is that we take two elements, we take the difference of them, and then we take the norm of the difference, and that's going to tell us an idea of how far they are apart. In quantum mechanics, since the inner product is in terms of probability, the distance essentially tells us the difference between two elements in terms of probability of transition. Okay, so what is a Cauchy sequence? Well, first of all, it's a sequence. So we have countably many vectors, one after the other. And what we can do is define a distance between any pair of vectors in the sequence. So we can have this table where we can get one element and the other elements, and we can calculate the distance between all the different combinations, right? So we have this infinite table of elements, of rows and columns. Now, this sequence is a Cauchy sequence. If whenever we pick an R, that basically it functions as a distance cutoff in terms of how far things are apart, we can find an N such that after that N, all the elements are close to each other, that the distance between them is less than R. So what happens is that we picked an R, we found our N, and all the elements here in this infinite table are less than R. So we can imagine that as we progress down, the values become smaller and smaller. And so this is the criterion of convergence, which it's not very easy to understand what it means. So can we find something that it's a little bit easier, that makes a little bit more sense? And of course we can. So if we have an Hilbert basis, right, and this is again a set of orthonormal elements that span the whole space, then the linear combination of those elements is in the Hilbert space, and therefore it's a Cauchy sequence, if and only if the sum of the square of the components converges, right? So essentially, the requiring that the Hilbert space is the space is closed under Cauchy sequence, and therefore is a Hilbert space, means allowing all the sum of a linear combination of elements such that the sum of their coefficient converge. And of course, if we imagine these as a normalized space and these are probability, this will sum to 1. So we are kind of assuming that we can take all the probability distributions that sum to 1. So this looks like a very reasonable mathematical constraint, specification. But now the question is does this make physical sense, or does it bring in elements in the space that are sort of physically questionable? So suppose we have an operator n that counts the number of particles, and suppose that these i's are the eigenstates with I particle, right? So these are vectors in the Hilbert space, and assuming that we only have the degree of freedom that counts the particle, that's the only that forms a complete basis. And we can then define the expectation of that operator. And how do we do it? Well, in the usual sense, it would be this this element, psi and psi. And we can express this in terms of the basis. We take this psi and express it in terms of the basis. We have an I applied to n, which, since I is an eigenstate of n, just makes the I comes out, the eigenvalue comes out. And now this is just the component of psi on the ith element of the basis. So the expectation of n is simply the sum of I times the norm of the component. Now, what we had is that psi I square, the sum of psi I square, are guaranteed to converge, but now we are multiplying by an I, and so now this is no longer guaranteed to converge. So, for example, if we take psi I to be square root of 6 over pi I, and we calculate the norm of psi, we have 6 over psi square over I square, and the series I over I square converges to pi square over 6, so these cancel out, and we just have a nice unit. So this is actually, the components give us a normalized vector, which is nice. And now we take an expectation value of this, and we have to take the psi squares, which is this, and multiply it by the I. And what happens is that now we have 1 over I squares I, and this simplifies. And what was the series before was 1 over I squared, now becomes 1 over I. 1 over I is the harmonic series which diverges, and so the expectation of the number of particles is actually infinite. So there are pure states in the Hilbert space for which there are literally infinite many particles. And this, of course, it's not good. Now, this is actually a much bigger problem because there is a theorem that tells us that every continuous linear operator defined on the whole Hilbert space is bounded. And so if we want something that is unbounded, then it cannot be defined on the whole Hilbert space. What does that mean physically? If we take operators like position, momentum, energy, number of particles, all these are unbounded because there are cases in which the value can be always bigger and bigger. And therefore, there must be elements in the Hilbert space such that those the expectation for those elements, for those observable, is either infinite or not even well defined, which again, it's physically is not good. So we have this tension is that we on one side we need infinite dimensional spaces to model quantities that are unbounded, that have no upper limit. But if we're using Hilbert spaces, well, Hilbert spaces forces us to include objects for which the expectation of those quantities are infinite. And so if you're using Hilbert spaces to model quantum mechanics, you should be aware of that and you should be careful in interpreting the physics that you're getting out of this. Okay, so this was the case of, we saw now the case of a discrete unbounded operator. Now we want to understand what happens to continuous operator like position and momentum. So we were able to extend this infinite sum in the case where the basis is infinite, that we have, let's say, the eigenstate, for example, for a number of particles. Now we want to do the same for a continuum. We want to describe something like position, and position has a continuous of cases. And the naive extension would be, well, we just take this sum and transform it to the integral, and we change the eigenstate of number of particles or discrete operator to something that is continuous. And this is actually what we do a lot of the time when we're doing computation in physics. In books you will find this. And the issue is that this does not quite work, and it does not quite work in some subtle cases. So sometimes it works, sometimes it doesn't, and so I think it's better to understand what actually goes wrong here in both the mathematics and the physics. So what happens is that this psi here, like this psi square, this component, is really a probability, right? This is going to be the probability of finding the element in this eigenstate. But when we do a psi x square, we get a rho, we get a probability density, right? So this is a probability density, and these don't work the same under change of variable. They work differently. So, for example, suppose that we change our observable from O to A, and we have a map that for every value of O we get a value of A. What happens is that the eigenstate of A that corresponds to the eigenstate of O is exactly the same eigenstate. And how we can see that? Well, because if we do the inner product of OI with psi, we really get a probability. And the probability of getting O is going to be the same as the probability of getting A. So this and this are actually the same thing because they have to give us the same number. But if we do the same thing on a continuous variable, so we go from x to y, what's going to happen is that we are going to have the square root of the Jacobian of the transformation. This because the probability density, right, is defined over a volume, and now the volume is changing during the transformation. In terms of units, right, this would be probability over distance as defined in x. And now rho y needs to be a probability over distance defined in y. So if you change units, you are going to have a factor that it's going to add up. So what happens is then is that if we do the inner product between x and y to get our probability density, is not going to be the same as the inner product between 1 and psi, y and psi, because you're going to have a factor of a Jacobian. And this means that the units, and you need to be careful about units, and really these objects work differently. So this is the first problem, which I think is the more physical one, is that, again, you have to keep track of units, you have to understand what's going to happen when you're doing these inner products. But there is a much bigger issue that all these things mathematically is not quite defined as you think it is. because the delta function, the x, right, the eigenstate of x, are not in the Hilbert space. And this is something that confused me a lot, and because I thought they were, because by reading books and reading on paper, it sort of it gives you the impression that that's the case, and it's not the case. And what I personally was confused is that the Delta-Dirac is a limit of a sequence of the Gaussian. So I thought, okay, the Dirac is a limit of a sequence, so therefore it's going to be in the Hilbert space. But the issue is that it's not a Cauchy sequence, right? It's a sequence, but not a Cauchy sequence. It does not converge as the Cauchy sequence required. Now, the calculation is a little bit intense, so it doesn't really fit here, but at least I give you the idea of how you construct it. So if you want, you can go and do it yourself and convince yourself and check my math to see if I'm actually doing the correct thing. So you get, we have a wave function here that corresponds to the square root of a Gaussian, such that when you do a psi bar psi, the probability density is actually a Gaussian. So you have this factor of 1/2 becomes a quarter here, and this square root becomes a power of 1/4. And so what we are saying is that the limit as sigma, as the variance goes to 0, we get a delta Dirac. Now, of course, then we can make a series where a sequence where our variances keep shrinking and shrinking and shrinking, and if we calculate the distance, we get this expression 2 multiplied by 1 minus the square root of 2 sigma 1 sigma 2 divided by the sum of the variances. Now, if we go to 0, right, if we make one of these elements go to 0, either sigma 1 as sigma 2, right, as we go farther and farther in the sequence, this term here is going to converge to 0. Therefore, this whole thing is going to converge to 2. So as we shrink, the distance actually remained locked and remain greater than any possible r that we might choose. So the distance cannot be made arbitrarily small. So this is not a Cauchy sequence. The Delta-Dirac, the eigenstate of position, are not in the Hilbert space, right? So talking about the inner product between eigenstates of position and everything, it's a little bit ill-defined in the Hilbert space. You need something else. And now you might say, oh, but this is kind of a mathematical detail. Well, yes, everything is a mathematical details, but that's exactly the case. We have to understand whether these mathematical details map to physics or not. And if you were to consider the Delta-Dirac really as a basis, you would have sort of a conceptual problem. So, which is, what is the countability of the states? Like, what is the dimensionality of the Hilbert space we are considering? So suppose we have a harmonic oscillator, right? In a one-dimensional harmonic oscillator. This is going to have the eigenstates of this harmonic oscillation are going to be the Hermite function. And these are countable, right? There are discrete energy levels that you can step up and down, and each of them is going to have an eigenvalue that is going to be 2n plus 1 h bar over 2 times omega, right? And so there are countably many eigenstates of this this Hamiltonian, and these are going to form a basis of the space. So the space is a countable space, so that the elements of the base are countable. And so if you really thought as the eigenstate of position as being eigenstate, you would have this contradiction. Is the dimensionality of the Hilbert space countable, or like the continuum? Because there are more points in the continuum, there would be more eigenstate of position than there are for the harmonic oscillator. So what happens is that really the basis is still countable, and mathematically the countable discrete space that we're seeing before is exactly the same as the space of the continuous, the space for a continuous variable, the space of integer functions L squared. So this, again, mathematically is important, but also physically is important, because what happens in quantum mechanics is that even the continuum behaves like the discrete. And the fact that it behaves like a discrete, for example, allows us to define von Neumann entropy, right, on those coefficients, and since the basis is discrete now, you don't have the issue of the coordinate transformations, and so everything sort of, even on the continuum, work a little bit like a discrete. And this is one of the key features of quantum mechanics. And so if you really would take literally the fact that you have eigenstate of position, you would miss out, as I did, with the fact that actually one of the key point of quantum mechanics is treating the continuum a little bit in some sense like the discrete. Now there is a further observation that again it's a little bit counterintuitive. If we take a two-dimensional harmonic oscillator, right, we would have again the tensor product of the Hermite functions on x and y, right? So we still have a set of bases that are identified by two numbers. And because these two numbers are still integers, you can do this diagonalization, and you can still have a countable basis, because you can count your bases just by going through this diagonal, which is a sort of common technique in mathematics. So what happens is that both of these spaces, the one of integral function of r squared and the one on integral function of r, they're both Hilbert spaces that are countable, and you can create a unitary transformation from both of them, between them, and therefore mathematically really they're the same space. Mathematically, if the base is countable, which means the Hilbert space is separable, and there's good reason to think that non-separable Hilbert space are even less physical, but they really do not even consider them. Like all of those separable Hilbert spaces that have a countable basis are actually the same space mathematically. They are isomorphic. And again, this is counterintuitive because physically kind of does not make sense that we can take the information on 2 degrees of freedom and sort of repackage it in a single state for a single degree of freedom. So this part I don't quite know whether it's a physical insight or again it's a byproduct of the fact that the math is using some space that has some slightly unphysical things. So, but again, mathematically, this is what the math says, and again, you should at least be aware of that. Okay, at this point, some of you might have said, oh yeah, I know that the eigenstate of position are not in the Hilbert space, so they are in this rigged Hilbert space and some stuff, and that fixes everything. Well, it does not fix everything, but at least you should know exactly what that thing is. So, we have the Hilbert space here, and we said the Hilbert space defines a criteria of convergence. Inside the Hilbert space, there is something called the Schwartz space, and the Schwartz space is the set of infinitely smooth functions that converge fast, which means they converge faster than any polynomial, right? So if you take the expectation of any polynomial, you get something finite, and you can think it basically that they go down at infinity, they go down like an exponential. So, for example, a Gaussian would be in the Schwartz space. So every element in the Schwartz space is in the Hilbert space. The nice thing about the Schwartz space is that because it goes down faster than any polynomial, and because it's infinitely smooth, you have finite expectation for all polynomial of position and momentum, which is something probably desirable. Not only that, those expectations uniquely identify as force functions. So if I gave you all the expectation value of all polynomial position and momentums, you would be able to say, aha, this is the only Schwartz function that actually satisfies those constraints. Again, to me, this makes sense physically, because what happens is that when we're doing measurement, we are characterize something, there is a technique that is called quantum tomography that basically allows you to reconstruct the state from the measurement of expectation values. So expectation values are things that we can measure, of course, if they're finite, and then this means that we can always reconstruct, at least ideally, right, elements, the state of the Schwartz space from experimental data, which again is a good property to have. The Schwartz space is also closed under a Fourier transform. In fact, it's so special, it has such an intimate connection with the Fourier transform, right, which is what we use from going from position to momentum representation, that the theory of Hilbert spaces and the theory of temporal distribution, which is where the Delta-Dirac lived, are defined starting from the Schwartz space. So the Schwartz spaces are the test function, are really the things on which everything else is defined. Not only the Schwartz space is dense in the Hilbert space, meaning that the Hilbert space can be understood as the closure of the Schwartz space under the Cauchy sequences. So if we have any point in the Hilbert space, it can be approximated by a sequence of Schwartz functions. So again, everything then that it's we define a Schwartz function in terms of the physics fully define the physics that is in the Hilbert space. And the space of temporal distribution, which is the dual of the Schwartz space, which basically is the space of all the linear operators that can be defined on the Schwartz space, is also can be understood as containing all the limits, including the Delta-Dirac of the Schwartz space. Again, all the limits in some sense. So really the Schwartz space is a subspace of the Hilbert space. The Hilbert space is a subspace of this temporal distribution. And all the physics is already defined in the Schwartz space, which again makes me think that this is really where the physics is defined. Now, these three spaces together are typically called the Gelfand triple or a rigged Hilbert space. Now, rigged here does not mean that it's cheating. It means rigged, fully equipped, like a rigged ship. So the idea is that the Hilbert space is fully equipped. It's rigged and ready to sail because it also has a Schwartz space and the space of temporal distribution. So when we're using a Delta-Dirac and those inner products, those inner products are not from between the Delta-Dirac and the the elements of the Hilbert space are not really the same inner product that you would have here on the Hilbert space. They're different things, they're different objects. And again, you should be careful of how to use them because they work differently. They give you probability density. You are taking two things that live in different spaces and put them together. You are bound to bump into problems. So at least you have seen some of this thing and you at least have a sense that this whole thing is a big mess. Okay, so let's close up. We need infinite dimensional spaces because we have a bounded operator like number of particles and because we have continuous operator like position, momentum, and so on. But a bounded operator are not defined on the whole Hilbert space. So if we take Hilbert space, you have this problem. Eigenstate of position are not really in the Hilbert space, so they are temporal distribution and do not form a basis in the same sense, right? When you go in the space of Hilbert, temporal distribution, there are all these other features, the things that you can do, but again, you're extending even more the space, and therefore you're going to find even more things which are not really states. There are different types of objects, and again, you should be careful of how you interpret all that math. The space of wave function, the square integrable function, has a countable basis. That is the eigenstates of the harmonic oscillator, like the Hermite function. So you shouldn't really think about the wave function having a continuous basis, because otherwise you're going to get into trouble. So with that said, be careful. I think that this whole area sort of is one of the hints that perhaps we don't have the correct mathematical structure. And by correct, I mean something that it's physically meaningful, where every object actually maps to some physical entity. So every vector in the Hilbert space maps to one physical state, is representing something, and that is also mathematically precise, right? We need both. We need something that where all the elements of the space are physical objects, but also that the whole thing is mathematically rigorous. And I really think that that the foundations of physics should really look more carefully at these issues, which is something that I do in my research assumptions physics. So thank you for your attention, and I hope you find this at least interesting.